In general, we're going to quickly go through the different types of synthesis reactions. For each of these 6 reactions, I'm going to list the reaction type. I'm going to give you a general form and a definition. Our first type of reaction is called a synthesis reaction. In a synthesis reaction, 2 substances are going to form a new compound. Now, these are usually elements, but they don't have to be elements. They could also be compounds. But in general, we have thing A plus thing B is going to react and form compound AB. And usually they're elements, but sometimes they're not. For the examples, I have magnesium plus oxygen. Well, magnesium and plus oxygen, the magnesium and oxygen are going to combine. You have to write the correct formula over here. Magnesium is a +2 cation, oxygen is a -2 anion, +2 -2. MgO is the compound for magnesium oxide. It's not a balanced chemical reaction, but we're not worried about balancing right now. We're worried about being able to make these predictions. Example number 2. I have iron and oxygen, and I'm going to assume that this is iron +4, although I don't think there really is such a species. But we have iron and we have oxygen coming together. This iron's a +4 and this oxygen a -2, so when we do the crisscross, it'd be Fe2O4, but those numbers reduce, and it's simply just FeO2. I have two -2 charges to balance off the +4. Again, this one is a balanced chemical reaction, but don't think that we just take this O2 and stick it over here on the side. We're writing the correct formula. In this one, we're assuming Fe +3, and we have iron, Fe, and we're combining with oxygen. Iron's a +3, oxygen's a -2, so we have to crisscross these. So this is Fe2O3. This is your common ordinary rust. My intent is to go quickly through these to reduce space on the disk, and I'll allow you to pause to get all these things down. If you have questions, you can ask in class. We're going to go on and we're going to do the second type of chemical reaction. These are called decomposition reactions. They're basically the reverse of a synthesis reaction. I have one compound on the left, and it's going to break down into parts. One thing on the left, 2 or more things on the right. Generally, things are going to break down into their elements, but I have 2 down here at the bottom that it's not necessarily the case. So we have water, we run an electric current through it, and it's going to break down into hydrogen and oxygen gases. Well, we got to write the formula for hydrogen and oxygen gases correctly. So the formula for hydrogen gas, again, that's a diatomic, so it's H2 plus O2. With mercury oxide, symbol here stands for heated, so you put it under a Bunsen burner and you heat this mercury oxide, and it's going to decompose, and when it decomposes, it's going to come down to its elements, mercury and oxygen gas. Notice how the O2 gets written over here because it's just oxygen gas. When it's by itself in nature, it's written properly with an O2. The last 2 are special case rules. They're the metal hydroxides and the metal carbonates. The metal hydroxides, if you have a metal, which calcium's a metal, and I have a hydroxide, so it's calcium hydroxide, those are going to break down and it's going to form the metal oxide and water. Well, the metal oxide, so I've got calcium, Ca, and I've got oxygen, that's the oxide. Calcium's a +2, oxygen's a -2, so CaO is the proper formula for the oxide of calcium, and our other product is going to be water. All that's basically doing here is that we are just taking off a couple of we're taking off the H2 and an O, and we're leaving behind one oxygen over here. So we get calcium oxide and oxygen gas. In our next decomposition, this is the metal carbonate rule, and I have aluminum carbonate here, and it's going to break down. When it breaks down, it forms the metal oxide and carbon dioxide. Notice how these are very similar. Both of them are forming metal oxides. So we got to write the formula for aluminum correctly. I'm sorry, the aluminum oxide correctly. So we have aluminum, and it's going to combine with the oxide, and I'm going to space that over just a little bit more because we may have some crisscrossing. Aluminum is a +3 and oxygen is a -2, so that when we properly write this, I'm losing my stuff here, it's Al2O3, aluminum oxide. And then we have plus CO2, just like that. Alright? So, here we go. Aluminum oxide plus CO2. So there's the oxide of aluminum and carbon dioxide. Moving on to the third type of chemical reaction, we have a single replacement. There's 2 types of single replacements. The basic single replacement is I have element A, usually a metal, and compound BC. The B and the A are going to trade positions. and B is going to be by itself, and A is going to bond with whatever C was. The other type of reaction that does something similar is with halogens, but on the halogens, it's the anions, the back ends, that switch positions. And the example here is I have compound Y plus AX yields compound element X plus AY. Well, in this case, it's the back ends, the Y and the X, that are changing positions. And then usually that's caused by halogens, although sometimes other gases can do that, notably oxygen. So in our examples here, we have aluminum and lead. Those are the two things that are going to trade positions, and lead is going to be by itself on the right-hand side. The aluminum is going to bond to nitrate, so aluminum is going to bond to the nitrate, NO3. Now, aluminum is a +3, nitrate is a -1, so I have to do my crisscrossing, and aluminum nitrate is AlNO3. Over here, we have sodium plus water. And the best way to do this, a lot of people think, well, it's just the sodium and the hydrogens that are trading positions and you get sodium oxide, but that's not what really happens. It turns out that not all of the hydrogens gets traded. It's the sodium and only one of the hydrogens, and the sodium is bonding to not just an oxygen, but a hydroxide group. So when this replacement is done, we get hydrogen gas as our lone extract, hydrogen, and the other thing that we get off of that is the sodium bonding to the hydroxide. Sodium is a +1, hydroxide is a -1, sodium hydroxide. And remember, I wrote the H2 because that's a diatomic gas in nature. Remember, there's 7 of those. So again, we have the sodium and one of the hydrogens trading positions, single replacement. In this one, I have an example of halogens, and in this one, the fluorine and the chlorine are going to trade. So chlorine trades with fluorine. So chlorine gas, again a diatomic, is going to be by itself. And the hydrogen then is going to bond to the fluorines. Hydrogen is a +1, fluorine is a -1, so HF is hydrogen fluoride, and that's written correctly. Now, they're not balanced chemical reactions. If I wanted to balance those off, I'd have to put a 2 here and a 2 over here, but I think you're experienced enough on balancings. If there's such a thing as a single replacement, there's also such a thing as a double replacement. In a double replacement reaction, having some issues here. In a double replacement reaction, we have two compounds, compound AX and compound BY. And what's going to happen in this is that the A and the B are going to trade positions. And I get compound BX and compound AY. So usually I think of it as the two metals, because usually it's the metals that are in positions A and B, although sometimes it could be hydrogen, as I show in the next example. They're just going to simply trade what they're bonded to, but you got to write the formulas right. So in this example right here, and I just draw the arrows as a teaching tool, the potassium and the lead are going to switch positions. So the lead is going to bond with the iodine. And when we write the formula, we have to figure out what type of lead this is. We know nitrogen is a -1, and there's 2 of them, so the total charge from the nitrates is -2. So this lead over here must indeed be a +2 lead. +2. So when I write my formula correctly, it's going to be, and I can't find out where I'm at here, it's going to be PbI2. Let me undo those and see if I can put them back here. Here we go. PbI2 plus the potassium is going to bond to the nitrate, and we get KNO3. Potassium is a +1, nitrogen is a -1, and so it's properly written as KNO3. So we're good to go on that one. So everything's written correctly, and we're good to go. I should just space those together better, but I didn't. In this one, it's going to be the iron and the hydrogen that are going to trade positions. The iron is going to bond to the chlorine, and we get FeCl. This iron over here is a -2 because sulfur is a -2, so iron has to be a +2. So this is iron 2, so for chlorine I need to have 2 of those on there, so that's FeCl2. And my other compound on there is going to be the hydrogen bonding to the sulfur, and so I get hydrogen and sulfur. Hydrogen's a +1, sulfur is a -2, so I do my crisscross H2S. That gives you your nice rotten egg smell when this compound is a gas and comes out. So, double replacement reactions, I have 2 compounds and the front ends are trading positions. You can just as equally think of it as the I and the NO3, the back ends, the anions trading positions, but you got to think of it one way, and that's just how I think of mine. Acid-base reaction. I disagree calling this its own type of reaction. It's just really a double replacement reaction in which you have an acid and a base and it makes water. When recognizing acids, all acids, well, I shouldn't say all acids, but one of the basic definitions of acids is that they start with hydrogen. And the basic definition of bases is that they end with OH. So you recognize your acids, you recognize your bases, and the hydrogen is going to trade with whatever thing B is, and so you're going to get compound BX, and the other compound that's made some water. So really, this is just a double replacement reaction that makes water. So in our example here, I have hydrochloric acid plus sodium hydroxide, a pretty basic chemical reaction. The hydrogen and the sodium are going to trade positions. The sodium is going to bond to the chlorine, NaCl. And my hydrogens are going to bond to the OH groups, and so you form hydrogen hydroxide, HOH, which is the same thing as H2O. There's my water. The other compound that's made besides water in these is what's chemically known as a salt. And there's many types of salts, not just table salt that you're all familiar with. All right. Last type of chemical reaction I saved to the end here. And this one is a combustion reaction. Combustion reactions are the easiest to predict because they're always the same products, because we're always going to assume there's enough oxygen gas supplied. You have to start with some kind of hydrocarbon. A hydrocarbon is something that has carbon and hydrogens in it. Usually, or no, I shouldn't say usually, it doesn't have to, but sometimes it has oxygen with it. So technically there doesn't have to be oxygen. I got an example of that down here. But you have a hydrocarbon. The plus O2 means that it's burning, and so you're combusting it, and the products are always carbon dioxide and water. So the O2 is an indicator of combustion reactions. Now if we went back and took a look at the synthesis reactions, these are not combustion reactions. Yeah, you're burning the magnesium and you're burning the iron, but your products are not carbon dioxide and water. Combustion reaction has to be a hydrocarbon, and you get specifically carbon dioxide and water on that. So products of this, carbon dioxide and water. Having all kinds of problems. Carbon dioxide and water. And the products down here are carbon dioxide and water again. And you'll note that I'm writing those backwards because it doesn't matter the order that you write these, as long as you got everything on the left that's supposed to be on the left and everything on the right that's supposed to be on the right. Alright, that's a quick crash course. Hopefully with some practice you can get used to identifying these types of reactions and then finally making the predictions. Thank you for your time.